So I'm considering a particle of mass m, and suppose it is moving along a circle about this line, we call it axis, and it is tied to a string. The one end of a string is fixed at this point, and suppose the length of the string is r, and the velocity of this particle at an instant is suppose inward, and its value is v. Now the angular momentum denoted by L vector is defined as r cross mv, and the value of this, the modulus of L vector, will be simply r into mv, because r and v are perpendicular, and its direction is as shown in the figure. Now as the particle moves, this L vector will also move along with the particle, and it's doing so like this. So both will move like this. So L vector is always perpendicular to r vector, and as r vector moves, so does L vector. So here L vector is not a constant vector, it is changing its direction, and therefore it is a changing vector. And whenever L vector changes, there must be a torque acting on the system, and we have one important relation, that torque is equal to the rate of change of angular momentum. So if we resolve this L vector into two components, suppose Lx and Ly. So imagine this L vector is rotating along this circle, the tip is touching the circle. Then if you keep on resolving the L vector into two components at every instant, then you will find that Ly is always the same, while Lx is rotating. So L vector is changing because Lx is rotating. Now whenever a vector having its magnitude constant changes its direction continuously, its rate of change is the vector, the magnitude of that vector, into omega, the angular speed with which it rotates. So here Ls vector is rotating with angular speed omega, and suppose we take two positions of Lx vector in a small time interval dt. It's covering an angle d theta. So this is for dt time. This is initial position of Lx vector, this is final position of L vector. So initial plus change gives final. So change in Lx vector is this, shown in red here, and this is dl vector, change in L vector. And if you find magnitude of this, it will be L vector Lx into d theta. And how it comes about, imagine a circle here of radius Lx. We have to find the magnitude of this vector. So this is a chord here joining the tips of the two vectors. So it's a chord, and since d theta is very small, this chord is almost equal to arc, and arc is radius into angle. Here radius is Lx and angle is d theta. So this is the magnitude of dl vector, and its direction will be perpendicular to Lx. If you reduce this d theta further and go on reducing, so finally this the change in vector dl, this will become perpendicular to Lx. So as d theta tends to 0, the direction of this dl vector will tend to be perpendicular to this Lx vector, and its magnitude will be Lx into d theta, and if we divide by dt, we'll get Lx into d theta by dt, which is Lx into omega. So d by dt of Lx we found was Lx into omega. And what was Lx? Lx was the cos theta component of L vector, which was r into mv, found earlier. So cos theta component is r mv cos theta. So multiply this Lx by omega. So this is d by dt of Lx, and it is perpendicular to Lx, and in this figure it will be inwards, because this Lx vector is rotating and this tip is going inward at this instant. Therefore the rate of change of Lx is inward, and the rate of change of angular momentum is torque. So we must have an inward torque of this magnitude. So this is the result we have obtained, that for this particle to move along the circle, an inward torque of this magnitude must be acting on it. Now If we consider the forces acting on it, the forces are mg and tension. Tension on extending will pass through A, so it will have no torque, while mg, if you extend it, will have a perpendicular distance, and the perpendicular distance will be r sine theta, so its torque will be mg into r sine theta. So if everything is on the right path, we must have these two to be equal. So if we equate these two, writing omega as v over r0, the angular velocity is v over r0, because r0 is the radius of the circle along which the particle is moving, and on solving we get mg tan theta is mv square by r0. Now we have to verify this expression, and for that we'll apply Newton's law on this particle. So we have two forces acting on it, T and mg, and it's moving along a circle. So T sine theta will be a component towards center, so that should be equal to mv square by r means r0 here, while the other component, that is T cos theta, that should be balanced by mg. And if we divide and find tan theta, we'll get this result, which is equal to the result we obtained earlier. So this verifies the whole situation. So we have verified a very important relation, that is d by dt of angular momentum is equal to torque.